combination of cells is same that of combination of resistor and combination of capacitor. So there are two methods to combine the cells as series combination and parallel combination. So first of all, series combination. Okay, so now let there are two cells. Basically this is two cells having the EMF, we write E1 and internal resistance R1. Here is the terminal A and another cell. This is connected in series having the EMF E2 and internal resistance R2. This terminal is suppose B, sorry, this is C and this is B. And in our previous video we see that V is equal to EMF minus I current into internal resistance. So for AB, potential difference across AB for this terminal, basically this is VA minus VB is equal to, we know that this is E minus IR. So for this terminal EMF is E1 and resistance is R1 and the current is flowing in this circuit from here to here. This is I. Okay, then VAB is equal to EMF is E1 minus I for current and this is R1. This is equation number 1. Okay, for terminal BC, for terminal AB and this is for terminal BC, VBC is equal to VB minus VC and this is equal to, according to this formula, E2 minus IR2, equation number 2. Okay, now what will be the potential difference between the terminal AC? So again, potential difference across AC is given by VAC is equal to VA minus VC, and VA minus VB may be written as VA minus VB plus VB minus VC. So this is VB minus VB, basically this is VA minus VC. Okay, so we can write here like this, and we know VA minus VB is this. So using equation 1 and 2, so this is VAC is equal to VA minus VB is EMF of first cell minus IR1. Okay, this is plus VB minus VC is E2 minus IR2. Okay, so again VAC is equal to, this is E1 plus E2, this is minus I, this is R1 plus R2. Okay, now for equivalent resistance, internal resistance, let in these two terminal A and C, there are a single cell having the equivalent EMF and equivalent resistance. So for this, AC is equal to equivalent EMF minus I, same current is flowing in this is I and this is R equivalent. So this is equation 3 and this is equation 4. Now by comparing equation 3 and 4, we can write equivalent EMF is E1 plus E2. So comparing 3 and 4, this is equivalent EMF is E1 plus E2, and equivalent resistance is minus I, R equivalent this is minus I, so this is R equivalent is R1 plus R2. So this is R1 plus R2. If there are n number of cells having the EMF E1, E2, E3 and dot 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 En, having the internal resistance R1, R2 and so on. So this equation may be written as En and this is Rn. This is the equivalent resistance when the cells are connected in series. Now cells may be connected in parallel also. So now parallel combination. So first of all, let point A and okay, this is E1 and internal resistance is R1, this is E2 internal resistance R2, this is A and this is B. Now if current is flowing in this circuit is I, whatever be the direction according to circuit, so this current is divided into I1 and I2, but potential difference for both cells is same. So potential difference between A and B is the V. So potential difference is V across AB is V. Now we write this formula for A E1B for this path and again for this path. So for A E1B, this is V is equal to E1 minus I1 R1. So for this is I1, this is E1, this is R1. So this is E1 minus I1 R1. Okay. Similarly, for A E2 for this path, A E2B potential difference is same and this is E2 minus I2 R2. Now from here we can write I1 is equal to, this is I1 is equal to E1 minus V upon R1 and this is I2 is equal to E2 minus V upon R2. Okay, and from this circuit we know that I is equal to I1 plus I2. So again we write I is equal to I1 plus I2 and this is I is equal to we write I1 and this is I2, this is E1 minus V upon R1 plus E2 minus V upon R2. So if we take LCM, this is R1 R2, this is R2 E1 minus V R2 plus R1 E2 minus R1 V. This is I basically. So we can write R1 R2 I is equal to, this is R2 E1 plus R1 E2 minus V R1 plus R2. So now V R1 plus R2, sorry, this is small r, R1 plus R2, we take this side, and this is R2 E1 plus R1 E2 minus I R1 R2. So V is equal to R2 E1 plus R1 E2 upon R1 plus R2 minus I R1 R2 upon R1 plus R2. Now let us consider a single cell is between this terminal. So this is A, this is B, current I is flowing in this, and EMF is E equivalent and resistance is equivalent. So now this is equation number 1. For this equivalent resistance, this is R equivalent minus I R equivalent. So this is equation number 2. Now by comparing equation 1 and 2, by comparing equation 1 and 2, we can write equivalent EMF is this. This is R2 E1 plus R1 E2 upon R1 plus R2, and equivalent resistance is this. So equivalent resistance is R1 R2 upon R1 plus R2. Equation number 3, this is 4. Okay. Now we can write this as equivalent upon R equivalent, equivalent EMF upon equivalent resistance. So this is R2 E1 plus R1 E2 upon R1 plus R2 upon R equivalent. This is maybe R1 plus R2 upon R1 R2. So this is cancel. So equivalent EMF upon equivalent resistance, this is equal to R2 E1 upon R1 R2 plus R1 E2 upon R1 R2. So this is R2 R2 cancel, R1 R1 cancel. So this is E1 upon R1 plus E2 upon R2. And now there are n cells are connected in parallel, then this become En upon Rn. So this is the expression for the ratio of equivalent EMF to equivalent resistance. Now again from equation 4, again from 4, this is R equivalent is R1 R2 upon R1 plus R2. So we can write 1 by R equivalent is R1 plus R2 upon R1 R2, and this may be written as R1 upon R1 R2 plus R2 upon R1 R2. So 1 by R equivalent is 1 by R2 plus 1 by R1. This is 1 by R1 plus 1 by R2. This is the expression for equivalent resistance when the cells are connected in parallel. Okay, thank you.